In the last sections, or the last few sections, we introduced the idea of a limit by looking at how sequences can be used to approximate irrational numbers. Now we're going to turn our attention to how limits behave under various operations. So our students are probably already pretty comfortable with arithmetic rules for real numbers. But this time we're going to look at arithmetic of limits, which we call the limit laws. These are important because it allows us to see how approximations can introduce errors and how making multiple approximations across the length of a problem can accumulate to larger errors. So when we round numbers, this is an example of approximation, right? We saw this in section 1.3. So for instance, when we round pi down to 3.14, we had said that this is going to have an error bound of 0.01, right? 0.01. And that's because the distance between pi and our approximation of pi is less than 0.01. That's equivalent to saying we know that pi is going to be in between 3.13 and 3.15. Right? There's this bound in between there. And similarly, when we round 1/3 off to 0.3 rather than the 0.3 repeating that it's supposed to be, this is going to have an error bound of 0.1, and that's because the distance between 1/3 and our approximation of 0.3, I really should be using approximation symbol here. The distance between those two numbers is going to be less than 0.1, or equivalently, we can say that it's in between, right, 0.2 and 0.4. And so that's what our error bound is for each one of these individuals. Well, then what is our error bound if we were to approximate pi plus 1/3 as 3.14 plus 0.3? In other words, if we decided to just sort of round off each one of these individual terms, first round off pi as 3.14, and then round off 1/3 as 0.3, how big is our error going to be? Or how big could our error be when we do these multiple approximations throughout the course of our arithmetic? And well, I mean, we can actually kind of figure out what it is, right? Like what is the approximation going to be? 3.14 plus 0.3 is going to give us an approximate value. Well, it's going to give us an exact value, but it's going to give us a value 3.44. So this is saying pi plus 1/3 is approximately 3.44. Well, the distance between the number that we're actually looking for, pi plus 1/3, and the approximation that we're using, 3.14 plus 0.3, is going to be less than 0.11, which is just the sum of our two original error bounds, 0.01 plus 0.1. Okay, this is an instance of using one of those limit laws in action. So let's define those limit laws a little bit more carefully. Let's assume A sub n and B sub n are sequences, and that those sequences actually have limits, right? So that sequence of real numbers is actually approaching some fixed value. And let's say that the limit of the first sequence, the A sub n sequence, I should say the limit as n goes to infinity, is equal to some real number A, and the limit of Bn as n goes to infinity again is equal to B. All of these limits are as n goes to infinity throughout. The limit laws tell us that the following is going to be true. If you add the two sequences together term by term, so you create a new sequence where the first term is A1 plus B1, the second term is A2 plus B2, and so on, then that limit is going to just be equal to the sum of your two individual limits, A plus B. The difference law similarly says if you create a new sequence where we're just subtracting the elements of our original sequence term by term, so an minus bn, then the limit of that sequence is going to limit to a minus b. The constant multiple law says that if you take one of your original sequences, let's say we take the a sub n sequence, and you multiply each term by a constant c, then the limit of that sequence is just going to be that same constant c times your limit a. And that's for any constant, any real number c. The product law says that if we're going to multiply an and bn together, so term by term, multiply a1 times b1, a2 times b2 to create that new sequence, the limit, as expected, is going to be just the limit a times the limit b. The quotient of an over bn, the quotient of that sequence is just going to be a over b, as long as your b sequence is not limiting to 0, or is not equal to 0. The limit of the sequence a sub n raised to the p power, so if we took each term of the an sequence and raised it to the p power for some integer p, that's going to give us, a limit of a to the p for any integer p. And the limit of the pth root of a sub n is going to be equal to, as expected, the pth root of our limit, a. As long as a is greater than or equal to 0 whenever p is even. Right? We don't want to allow for negative square roots. So these laws just follow from the epsilon definition of a limit, along with an important result called the triangle inequality, and they help us to simplify the process of evaluating limits. So we should probably define the triangle inequality because it is very important, very fundamental in analysis. Triangle inequality tells us that for any real numbers a and b, the absolute value of a plus b is going to be less than or equal to the absolute value of a added to the absolute value of b. Now, you'll prove those in the exercises. We don't have to worry about that right now. We'll just sort of take it to be true, but we use it in a lot of different analysis proofs. So let's try to use the triangle inequality to help us to prove the sum law. And just as a reminder, the sum law says that if we have these two sequences, an and bn, where the first sequence has a limit of capital A, and the second sequence has a limit of capital B, then the limit of a new sequence where we add the a sequence to the b sequence term by term is going to have a limit of a plus b. So if this is true, then the limit of an plus bn is equal to a plus b. Okay, so we want to show that this is true using the limit definition of convergent sequences. So let's try to sketch out a proof here. Okay. In order to show that this statement is true, that the limit of an plus bn actually gives you a plus b, we must show for any epsilon greater than 0 that there exists some natural number, which we'll call capital N, such that anytime our index, little n, is greater than or equal to n, we have that the distance between our kind of approximation here, or the element in the sequence, and the actual limit that we're saying it's approaching is less than epsilon, right? Then the distance between an plus bn and a plus b should be less than our epsilon. This is what we need to do. So this is just really rewriting the limit definition of convergent sequence in terms of this actual problem. So how do we prove this? Well, this is a universal statement, so we have to show that this is true for any epsilon greater than 0. So we start off by saying, let epsilon be greater than 0, right? Let epsilon be some arbitrary positive real number. We need to prove the existence of this capital N, so that anytime we take an index bigger than capital N, the distance between our sequence and the alleged limit is less than epsilon. Well, how are we going to do that? How are we going to find that N? Well, we're probably going to want to use our assumptions, which is that the limit of the an sequence is A and the limit of the bn sequence is B, right? So, we know that, we know that by the triangle inequality, if we rewrite this a little bit, let's go up to the top and look at the triangle inequality. If we can rewrite this as like a plus b, we can we can say by the triangle inequality that that absolute value is going to be less than absolute value of A plus absolute value of B. So let's rearrange this and write it as a sum so we can actually apply the triangle inequality. I'm going to rewrite it as AN minus A plus BN minus B. So I'm just sort of rearranging, and you can check that this actually is equivalent, but I'm distributing the negative sign and then using the commutative property to say that this is equal to AN minus A plus BN minus B. And now, by the triangle inequality, I know that this is going to be less than or equal to the individual absolute values added together. So the absolute value of AN minus A plus the absolute value of BN minus B. So we're applying the triangle inequality here using this sort of first term AN minus A as our little a, and using the second term BN minus B as our little b in the triangle inequality. All right, so we'll be able to use this in our proof here. Now, because the limit of the A sub n sequence is capital A, and similarly the limit of the B sub n sequence is capital B, I know that for any epsilon greater than 0, I can find an index n such that after that capital N point, the distance between big A and little a sub n is less than epsilon, and similarly for the b's. Whoops, what happened to my b's here? Okay. Well, okay, that's great, but if I try to use that directly, I'm going to end up finding that this distance down here that we're looking for is less than 2 copies of epsilon, right? If I just try to apply this using this epsilon that we've chosen, I can sort of apply it here and get that the distance between AN plus BN and A plus B is going to be less than 2 copies of epsilon. I want it to be 1 copy of epsilon. So what I'm going to do is I'm just going to introduce a new epsilon. So we choose, or we define a new epsilon. I'll call it epsilon prime. Just let it be epsilon over 2. Because in the end, I'm going to show that each one of these is less than or equal to epsilon over 2, so that when I add them together, I get the epsilon that we're looking for in the proof. All right, so if we define our epsilon prime to be epsilon over 2, epsilon prime is still going to be a positive number. It's a positive real number. And so that means that by the definition, or by the limit definition, of sequences that we've already seen, that there's going to exist a capital N, and just for the sake of not confusing it with the N we stated up above, let's give it a different name. We know that there exists, first of all, there's going to exist, let's say, a K, such that for as long as like little k is greater than or equal to capital K, then we know that A sub little k minus big A is less than epsilon prime. And we know that there's going to exist, let's call it an M, such that if little m is greater than or equal to capital M, then the distance between B sub little m and B is also less than epsilon prime. Right, we're just using the limit definition and saying our epsilon prime is a positive real number, so there's going to be some point after which any element of our sequence is within epsilon prime of the limit A and the limit B. Now I'm just going to sort of put these together and say, okay, well, as long as I'm choosing my big N to be at least as big as the largest of K and M, then each one of these AN minus A and BN minus B's that we're looking for is going to be within epsilon over 2 of the limit A plus B. Okay, so we choose our N to just be whichever one's bigger, the maximum of capital K and capital M. All right, that's the N that we're looking for up here. We need to justify that if little n is bigger than capital N, then this distance that we're looking for between A sub n plus B sub n and A plus B is going to be less than epsilon. Well, because we've chosen our n to be at least as big as whatever one's bigger, k or m, then for any n greater than or equal to n, we have that an plus bn minus a plus b, which we've already asserted up above, up here, is going to be less than or equal to an minus a plus bn minus b. And now from here, we know that this one will be less than epsilon prime, and this one will be less than epsilon prime as well. And each one of those epsilon primes is just epsilon over 2. So that's epsilon over 2 plus epsilon over 2. Well, 2 copies of epsilon over 2 is just plain epsilon. And this is exactly what we were trying to show up above. Right? We needed to show that we could find that capital N so that for any n past capital N in the sequence, this distance between the an plus bn and a plus b is less than epsilon, and we did that here. And that completes our proof. Okay, so let's look at one example, just one concrete example of using the limit laws. If we have an is a sequence of 2 plus 1 over n, and bn is a sequence of 3 minus 2 over n, we can use this to find the limit of an times bn. And we can sort of do that one piece at a time. The limit of a sub n as a sequence as n goes to infinity. As n goes to infinity, this is going to be giving you a term at the end that looks like 1 over a super big number, right? 1 over a billion, 1 over a trillion as n goes to infinity. And 1 over a very, very big number is going to approach 0. So this is going to be 2 plus 0, which is 2. The limit as n goes to infinity of 3 minus 2 over n is going to be, well, 2 over infinity is also going to, or 2 over a very, very large number is also going to be approaching 0. And so this is going to approach 3 minus 0, so that limit's going to be equal to 3. And so the limit of the product, according to our limit laws, is just going to be equal to the limit, uh-oh, my pen quit working on me. It's going to be equal to the limit of the an sequence times the limit of the bn sequence. So it's going to give you that 6. Okay, so why does this matter? Well, the inequality that we used in the proof of that sum limit law can be applied if we consider the ans in our sequences to be approximations. So for instance, if your approximation a sub APPR of A has a potential error of E sub A, and then the error accumulation of, let's say, like the scalar product C times the approximation is going to be no worse than the initial error scaled by the absolute value of C. And so we'll see in the exercises exactly why this might matter to what you're teaching in your classes.